There we go. I don't think that's going to change anything, is it? No. I mean, it's functionally equivalent. Hi, my name is Josh, and this is Electronics Unscripted, where we take an intuitive and unscripted approach to DIY electronics. This video is an extension of the last video where we worked with my R2R DAC resistor ladder, where we worked to create a digital to analog circuit. And we played around with that a little bit, just showed that when we manually set the 8-bit digital value, we got an analog output that corresponded to 256 levels of analog output. Well, the next logical step is we all know that sound is just an analog value varying with time. And obviously, you know, toggling these guys here, I'm not going to be able to do things quickly enough to create actual sound output. We have another problem with sound output in that the output of the DAC chip is between 0 and 3.3 volts, and that doesn't work for audio output. Audio output needs to be AC. It needs to go between 0 and a max and between 0 and a minus max. What I've done is I've wired up my op amp again. The op amp is still in a unity gain mode, so it's serving as a buffer so that this circuit on this board doesn't weigh down the ladder with too much of a load that would distort the DAC's operation. And then we run it through an RC circuit to remove the DC component of this waveform. So I get 1.6 volts positive all the way down to minus 1.6 volts. I get this AC waveform out of this capacitor. That I can then use to drive an audio source. And what I've done is I've wired up a little 3.5 millimeter audio jack. We've got our little friend here, a very cheap little radio that has an aux in, and we'll get to that in a minute. So let's talk through what we did here. And I'm going to be unabashed. I'm no C expert. I can become a C expert if I need to. For this sort of thing, I don't need to, and ChatGPT is your friend. I went to ChatGPT and said, I want to use a Raspberry Pi Pico and generate audio waveforms, and what's the best way to do it? So what we arrived at was 128 samples per waveform. And the next value is the number of microseconds per sample. So let's walk through this program a little bit. The main loop here is just this little interrupt handler, and this handles a timer interrupt. So we set an interrupt that fires every TSUS microseconds, so every 4 microseconds the timer interrupt fires, and it runs this code. And all this code does is GPIO put mask is a way of kind of bulk updating these pins over here on our microcontroller. It just updates them all at once, and it uses that wave value that we calculated. So there is up here, this is our waveform data in 8-bit samples. So we have the number of samples, 128 samples, and we have an 8-bit value in each one of them, and then it copies them out. We just have a little block of code that calculates the wave table for a sine function. And then we have another one that does it for a triangle wave. The key is this interrupt handler, and it reschedules itself at the end of every time it runs. So it runs, it copies the right samples bits out to the GPIO ports, and then it reschedules itself to run in so many microseconds. So here we have 4 microseconds. And if we do the math on this, so 1 million divided by 4 divided by 128. That should give us 1.953 kilohertz for the actual frequency of the audio wave that we're going to output. So let's go ahead and run this code. You can see right here we have 1.95 kilohertz. We have a nice sine wave. It is 1.5 volts to minus 1.4 volts. So we've done a good job of getting rid of that DC offset. So the DAC is outputting 0 to 3.3 volts. This is putting out roughly 3 volts peak to peak. We have wired in our little guy over here. You should actually be able to hear that waveform. Kind of cool. Now we can change the frequency by changing the microseconds per sample. So if I go to 8 microseconds per sample, the frequency should go up. Oh, down. Sorry. If I go to 8 microseconds per sample, the frequency should go down. If I go to 1 microsecond per sample, the frequency will go up. And you can see that on the oscilloscope, and you can hear it with your ears. We've got 128 bits per sample. I'm going to turn that off so it's not annoying. If we zoom in here, we can see that it's relatively smooth. We're not seeing a lot of jaggities. That's because we're using 128 bits per sample. Let's go ahead and do a triangle wave here too. So we're going to uncomment out our triangle wave and just, I don't know, maybe we'll just overwrite our sine wave. It doesn't really matter. Great. Look at that guy. We have this beautiful, beautiful triangle wave. Isn't that cool? And it doesn't, oddly, doesn't sound all that much different than the sine wave. I'm not exactly sure why. 4. So this should change the frequency, make it go down a little bit. So that's a nice one. This is actually a pretty smoothly varying function, so that those 256 digital levels give us a good amount of granularity, and the fact that we have 128 samples per waveform means that we don't really have any kind of jaggedy steps here. But what happens to the sound and what happens to this waveform as we change the number of samples? So let's go down to 64 samples, but increase the time step by the same factor. We get the same frequency, right? But now we have half the number of samples. So are we seeing any more jaggediness? And we actually are. Look at that. So now you can see kind of the digital steps in there because we don't have as much resolution in the waveform. We're having to take larger and larger steps in between each sample. So let's go ahead and go down to 32 samples and increase that up to there. And you can see even more pronounced that stair step. Let's go ahead and go down to 16 and then 32 here and see what that does. Looks still very similar, so we're still getting a reasonable waveform out of this. So for just basic tone generation, you probably don't need a very high sample rate. Let's see what that looks like in the sine wave. Still, I mean, a pretty reasonable, serviceable sine wave here, right? Let's go even lower. Let's see what we can get away with here. Well, the sine wave, we might be a little limited. 64. So again, we're having the number of samples and we're doubling the number of microseconds per sample to keep the same frequency output. So we don't have to adjust our scope and we have the same kind of reference sound. That's not horrible, right? I don't think I'm going to be able to get away with 4 here though. Let's see what that does. That should look something like a square wave. I'm not, oh, I mean, it's not, again, horrible. Wow, that's fascinating. And let's try this for the triangle wave example, see what he does. Oh, the triangle wave looks almost identical. We've lost so much resolution there, it looks almost identical. Let's go back down to 8 and 64. 16, 32. There. So you can very easily see that digital nature of the analog output the DAC is giving us. Okay, so now what we want to do is we want to do something much cooler than play little sine waves at various frequencies. Let's play the music, let's let the music flow. I've got a little PCM recorded file here. I used Audacity to transcribe this into an 8-bit wave, which does a PCM encoding. That's pulse code modulation. So what that means is that they just take, for every 8-bit sample, they record the 8-bit value of that sample. I changed it to a 22 kilohertz sample rate, and that's mostly for size because my microcontroller doesn't have a lot of memory. This single wave of a couple seconds takes up roughly half the memory of the microcontroller. So I really had to kind of compress it by reducing the sample rate. So here is the sample. So basically once every 50,000 microseconds, what we want to do is we want to send this particular digital level through our DAC to reconstruct the audio waveform that is this. So I've got this in a little header file, and you can see how big this is. You know, it's like, you know, several thousand rows. Here we have the final size. This, of course, isn't working. I don't know if you're listening over here, you might hear a very high-pitched above the ground loop. It's just not working. I've modified our program to just read in the da-da-da-dum wave, and the index increments all the way up to da-da-da-dum wavelength. So basically every sample, it should read in a value from the da-da-da-dum wave and output it to our DAC, and then pause for that amount, that number of microseconds. So I don't have exact, it's supposed to be 22 kilohertz sample rate. And so I've got a pause of 50 microseconds. That works out to 20 kilohertz, which is close enough, but it's just not working. And so what we're gonna do here is take a look on our scope and see what we're seeing. We're seeing like nothing on the scope. I don't know why it's at like 100 volts. Oh, you can see, yeah, there's like just a little bit of a ripple here. So that's good. So that's what we're hearing, this very low amplitude. I'm assuming that's the sample rate. I'm not sure. There we go. So that's 5 kilohertz. Maybe I did my math wrong. 5 kilohertz. And that's very exact too. So it looks like, I mean, it honestly looks like we're playing some other levels there too. When you look at this here, I don't think I can zoom in much more, but it looks like there's more than just one level that it's setting. So, and it does look like there's maybe 4 values and then it's looping. So I wonder if maybe we're something wrong with the way that we're indexing this. So this is, it's just a index. So it's just repeating itself. I don't know, we can just be a little bit more explicit. There we go. I don't think that's going to change anything, is it? No, I mean, it's functionally equivalent. That's awesome. It's very quiet. Yeah, you can barely hear that. That's awesome. I don't know why it's so quiet. One thing is the input could be coming from, I have it, input coming from across this resistor here. Let's see if it gets a little brighter source there. There we go. That's better. You can see there's quite a lot of static there. That's super awesome. Let's try and change this delay a little bit and see what that does. It should slow it down. You can see here a lot more of the noise in there too. So let's go up. That's awesome. That's just awesome. So great, this has been our exploration in using a homebrew DAC, an R2R resistor ladder, our homebrew DAC, to generate audio waveforms and to actually make some music. Play us out, Beethoven.